plus R over 2L. Take a moment to convince yourself that that's legitimate, or to find the mistake and let me know. There's one particular class that's doing a derivation, it might have been this one, doing a derivation, work across the entire board. And they came up with an answer that didn't make any sense. So I knew the mistake was somewhere, and the student goes, oh, you made a mistake back there. So if you spot a mistake, let me know as soon as possible, as opposed to at the very end. So at this point, I now have cosine alpha in terms of little r and some constants. I can plug it into here, and I have a single variable, and so the calculus becomes, well, I'm not sure trivial is the right word, but the calculus becomes definitely doable. So I got my big M dr over r times this, my cosine alpha, L squared minus big R squared over 2LR plus little r over 2L. Hopefully I got that written down so that I can compare, just to make sure I haven't made a careless mistake. Got a slightly different form. I think it's good. So we'll end up with that. All right. Feel confident enough? So I now have it in terms of a single variable, r. I can now integrate over all the values of r. And so therefore, my force, the total force acting, the electric force acting on charge 1, is equal to the integral of my differential r, so that is the integral of, I'm going to distribute, oh, that m is a vector, technically. So in the first one, I get L squared minus big R squared over 2L times dr over R squared plus, distributing to the second one, I got big M dr over 2L, because my r's cancel out when I distribute to the second term. So let's do some integration. So basically, when you're integrating things with a plus sign in between it, I can integrate them separately. So I've got that vector M, 2L, those are constants also, L squared minus R squared times the integral of dr over R squared plus M over 2L integral of dr. The only thing that's missing are the limits of integration. When you're doing limits of integration, our variable is r. What is the smallest radius? What is the smallest little r possible? If you think about all the possible rings that we could have around this sphere, because we're basically going to integrate the total charge based upon the differential of the charge for each ring, what is the smallest little r possible?
Very top or bottom.
So the smallest would be
Very top.
the top. And what is the value of little r at the top?
0. 0.
I hope not. This charge is not sitting on the sphere.
No, big L minus, or L minus big R.
Yes. So the smallest value is L minus R. And what is the largest value of little r? At the bottom?
L plus R.
L plus R, big R.
Right.
the merging of two absolutely incredible disciplines, math and physics. You're not dreaming, this is happening. All right, so dust off a few more cobwebs. What is the integral of dr over r squared? Just put that on the side over here. So the integral of dr over r squared, or I prefer to write it when I'm doing it personally as r to the negative 2 dr. Mentally, I find that easier to work with than over r squared.
Negative 1 over r.
Let's see, so r to the negative 1 over, you said negative 1 over r?
Or I guess, negative r to the minus 1, or, sorry.
Or, pick your poison. It's one of, they're all the same. And the integral of dr. R. So, my first term over here, for the math purists in there, apologize for that, for the physicists in the group, yeah, it happens. M L squared minus big R squared over 2L times negative 1 over R from L minus R to L plus R plus M over 2L times R. That's 2L times R from L minus R to L plus R. Plug and chug, simplify, we're done. And for the math purists, sorry about that loss of the second parentheses there. So M L squared minus R squared over 2L times negative 1 over L plus R minus negative 1 over L minus R plus M over 2L times L plus R minus L minus R. Only constants left, that's a good feeling. I will say at this point, some students are disappointed by the answer. Just saying. Just trying to lower some expectations. All right, so what we have over there, I've got two fractions that I'm adding together. I've got negative 1 over L plus R plus 1 over L minus R, because I got the double negative. And so this becomes negative L minus R plus L plus R over L plus R, L minus R. So on top, I got negative L plus L, that's gonna cancel out. Then I got R plus R, so I got 2R on top. And on the bottom, L minus R times L plus R.
L squared minus big R squared.
So what I've just done is this piece right here. If we multiply times that, what? L squared minus big R squared cancel out. That's convenient. So my force, the electric force on that charge 1 becomes M L squared minus big R squared over 2L times 2R over L squared minus big R squared. And our term over here. L cancels out, R does not. That second time we made that mistake, that should be an L right there. And we end up with M over 2L times 2 big R. Plus M over 2L
times 2 big R.
Ah, so much simpler. Don't worry, we're gonna simplify it again, but Joseph, you look like you have a question about something. It could be my handwriting.
I got MR somewhere. I just don't see. So we had M2L.
Right? I miswrote, I had a little R there, but that was a mistake on my part.
Okay, I was just trying to figure out what happened.
We physicists laugh at the mathematicians, say, I can make that whatever I want it to be.
Yeah, that's right.
I don't know if you've seen the cartoon about why mathematicians are not invited to physics conferences anymore. The mathematicians are up there and say, let's assume the speed of light is 5 quadrillion meters per second. The physicist raises his hand and says, you can't assume that, it's a set figure. The mathematician looks at the physicist and says, oh, you can't assume that, we can. So it's about time we paid it back. Like most physics humor, mildly amusing, but rarely ever laugh out loud funny. So simplifying it here, that 2 cancels out with that 2, that 2 cancels out with that 2, that L minus R squared cancels out with that L minus R squared, and I am left with 2 big M R. And we're going to simplify it one step further because we have the value for M over there that we need to stick back in.
What happened to the L
To the L.
underneath the M?
Oh, thank you very much. Over L. Thank you.
Would it be MR over A?
Sorry?
Would it just be oh no, isn't it 2 L's on the phone?
That 2 cancels out with that 2, and that 2 cancels out with that one. The 2's canceled out. Because when I finished doing all that fractions, I had a 2R right there.
Is that an L beside the 2?
That's an L beside the 2.
What about the other one?
That's an L beside the 2. Sorry. I think I'm missing your question. Or is it a matter of reading my handwriting?
Why doesn't the bottom have 2 L's?
All right, so ignore these crossed out lines there. If I just went ahead and multiplied these fractions together, I'd have M L squared minus R squared. Oh, you see it? Okay. All right, so we were back to M 2R over L. I think I wrote it in slightly different order before, but that's what I wrote before, right?
You have the 2 in front of you, that's fine.
Yeah. I am assuming that the commutative property of multiplication still holds.
After all this, yes.
Again, if the mathematicians have been lying to us, we are screwed in physics. All right, so our big M over there is big P, which is just J hat K Q1 times sigma 2 pi big R over L times 2 big R over L. Close parentheses. This bit right here, that I'm circling that was my made up vector P. That P right there. So this would be the force. And that 2R over L at the end comes from this right here. So basically it's M times 2RL. Which is J hat KE Q1. Helps if I actually write the letters Q1 sigma 4 pi big R squared over L squared. Four pi big R squared, where have I seen that before? Well, more importantly, where have you seen that before?
The k sub e.
Pardon?
It's the other form of k sub e. It's 1/4.
Oh, no, no.
Not there.
That was 4 pi epsilon naught, 1 over 4 pi epsilon naught. All right, let's take it one step further. Remember that sigma is the surface charge density, which is Q divided by the area, or Q2 divided by the area.
Or Coulomb's constant.
Pardon?
Coulomb's constant? Didn't we use it in Coulomb's constant? The inverse of it?
Oh, Coulomb's constant?
Yeah.
Coulomb's constant's got an epsilon in it. There's no epsilon here. Yeah, we're not gonna, that KE is gonna stay KE,
Okay.
despite your attempts to want to get rid of it. We're talking about the area here. It said the surface charge density was constant, so the surface charge density of my band there is the same as the surface charge density of any spot I take. But we're talking about the overall charge density, because I'm using Q2 here, the whole kit and doodle. What is the area of a sphere? Surface area of a sphere.
4 pi r squared.
So this becomes Q2 over 4 pi big R squared. So Q2 equals sigma times 4 pi big R squared. Lo and behold, we have that right there. Include the sigma. So this becomes J hat KEQ1 big Q2 over L squared. All of that to come down to this. And where have we seen that before?
Yeah, it looks exactly like the original formula.
Coulomb's equation. What we have just done is shown mathematically that if I'm looking at a spherically symmetric charge, I can treat it like a point charge at the very center. And that is a shortcut, and it comes in handy quite a bit. A spherically symmetric charge can be treated like a point charge. If, and this is a caveat I did not mention just then, but I definitely want to mention now, and if outside the sphere, like Q1 is. Q1 is outside the sphere, and it looks at that huge spherically symmetric charge and goes, I'm going to treat it like a point charge. It is a convenient shortcut. Questions to hear before we talk about what if you're inside the sphere? Oh, I am sorry. You get to go on moving on, and it's, physics, math. Only thing we can make it more exciting is throw some history into it, or at least come develop a math equation to describe and be able to predict history. But alas, class ended 20 minutes ago. I couldn't see the minute hand from where I was because of the glare, and I saw the hour hand, and I thought, oh, it's a little bit before 9. We're still good. I guess it was a little bit after 9.